keep in mind that in this chapter, you'll heavily see hints of calculus. It will actually have the derivations within the chapter. You are not expected to go through, do the calculus. Okay? It's just there because later on in your career, you might want that. Right? And you might need it for something. For example, spectroscopy is a very, very much a quantum science. Okay? Everything you see, all the light you see, everything you see at all, that is spectroscopy, and that is quantum. Okay? Now, interestingly enough, the person that I learned this from used a. Did you know there's 3 different types of calculus that were independently created? Yeah. So Newton created his own form of calculus, and there's 2 others. And we use one form that's been standardized across most of the United States. However, some parts of Europe and Asia use the other forms of calculus. It has a dot for the derivations and partial derivations. It doesn't have the same symbols. And then you can do everything calculus can do. You can do matrices with various levels of easier or harder. Yeah. So remember matrices back way back in the day that you may have learned? No? They had the bracket, 4 numbers in them, and then you did the multiplications by. Yeah. So if you're going to do calculus in a computer, that's how you do that. The computer doesn't understand symbols. So, anyways, so this is going to be where we go into the structure of the atom. Again, I'm going to treat this as a non-calculus information. Right here, this is actually an oscillating charge. This actually represents a wave traveling through space. This right here is actually the propagation direction. These here are not directions in space. Okay? So I know that in your mind, you've probably thought of waves like you would think of waves on a bathtub, right? And the wave oscillations are in space. These are not spatial oscillations. Okay? That's not how like the wavelength for light or the wavelength for a particle actually works. Okay? There are probabilities to find these things in that propagation direction. Okay? Or another way of saying that probabilities to find something is also expression of its characteristics, right? So for example, expression of a magnetic field, expression of negative charge from an electron, expression of an X-ray light, okay? Expression of a Wi-Fi signal, right? Wi-Fi signal is also microwave radiation, right? Okay, and so this right here is going to be Maxwell's depiction of that light. Again, it's a perpendicular oscillating electric and magnetic fields. These are actually at right angles from each other, and they form a right angle whenever you have, for example, a... has anybody ever used like electromagnet? Yeah? Yeah? Okay, so like an electric magnet, the electricity is going through the wire, right? The magnetic field, however, is actually perpendicular to the wire. Everybody notice that? Okay, same sort of thing happens whenever you're talking about electricity. The power actually is put out from the electromagnetic waves, which are perpendicular to the direction the electricity is actually flowing. Okay? Or for example, the power lines, they have a perpendicular relationship between the signal coming out of them and the direction the electricity is flowing, right? Okay, anyways, so this right here is how these things are related. So the speed of light equals the frequency times the wavelength. The frequency is how often, if you were to monitor a single point in space, the peaks pass that point in space over a given time, typically 1 second. Okay? Frequency is typically represented in hertz. Does anybody know what hertz actually means? Okay, everybody has a car, right, that has rotations per minute? RPM? Okay. Hertz is 1 over seconds. So it's peaks per second. How many times the peaks pass in 1 second. Okay? So if you have a smaller wavelength, the peaks will pass faster, right? Larger wavelengths, the peaks pass slower for a given amount of time. And all of that is because the speed of light is constant. Note, this is the speed of light through a vacuum because, again, we're measuring from point A to point B for speed, right? Okay, so let's go ahead and look at this in a slightly different figure. And this one, again, is just a more colorful, easier for me to discuss this figure. Again, you can measure the maxima or you can measure the minima. It doesn't matter. The wavelength will be the same either way. Anybody know what these letters are in here? Wavelength is denoted by what letter? Greek lambda. Okay? That's the Greek lambda. What's the frequency denoted by? Yeah, it's always put as a V because that's easier to type. It's not actually a V. It's a Greek letter. Okay? So this is the Greek letter right here, nu. Yeah. But nobody ever puts it because V is so much easier to type. And it looks like a V. Yeah. So the only one that ever usually gets typed is lambda if they're going to be special about it. And sometimes they're just going to shorten that down to a wavelength. Or WV for wave. And then length, L. So anyways, this is actually the properties of these various different types of light. Now, when we talk about these properties, these are typically going to be talked about for the non-metals. Okay? If you're talking about metals, you have to shift the entire frame of what these properties of light do for various different frequencies of light over. Okay? And so, for example, if we look at radio waves, they don't really have much effect. They can cause oscillations in certain substances where it will cause accumulated vibrations to happen. That would be like a radio transceiver. Okay? Over here we have microwave. Microwave typically is going to cause substances that are organic substances to rotate in space. And so rotations will match up with microwave frequencies, which will cause those to be absorbed. Okay? Is everybody good with that so far? Okay. Okay. So when I microwave my food, what am I actually doing? I'm taking water. I've taken a very powerful microwave radiation source. I've shot a central compartment with it, flooded it. Okay? Absolutely flooded it. Very powerful. Right? And then what I've done is I matched that up with the rotation of water. Okay? What would happen if all of you were right next to each other and you all started rotating? Woo! Start hitting each other, right? And bouncing off each other. Anybody seen a mosh pit? Yeah, same thing. So if we cause a bunch of random kinetic energy in a sample, what do we call that? Temperature or heat? So what temperature or heat actually is it's randomized kinetic energy. Okay? It's basically we have too many particles going in different directions and too many speeds to get a kinetic energy value. Okay? And so that's what we call temperature or heat. By the way, if I take all the particles in a sample, shove them real fast in one direction so they can't actually go in different directions, what would happen to the temperature? Let me ask a little easier. What if I froze everything in space? What would happen to temperature? Go down, right? Yeah. Specifically, it'd go very close to absolute zero, wouldn't it? If I could freeze everything perfectly, it'd be absolute zero, right? Okay, which is the Kelvin unit, right? All right, and that means no kinetic energy in that sample that's randomized, at least. Okay. Now, what if I do kind of the same thing, but I do it by taking everything and moving it in the same direction so there's no random component to it? That'd be kinetic energy, wouldn't it? And so I'd convert everything just to kinetic energy. There'd be no more heat or temperature, would there? Or at least very little. You can't perfectly do these things. Okay? And so when you've seen all these measurements, those are the two ways you've seen of getting down to the 0.004 Kelvin sort of stuff. When you've seen those in books and things. One is to take a matrix or grid, and then we cause everything to stop being able to move easily. The other way, and this is the more common one, is actually to shoot everything out at supersonic speeds in one direction. And then we suck away everything else that didn't go in that direction, and we're left with kinetic energy, no heat. Or almost no heat. Okay? Okay, so anyways, rotation is where we're going to be taking this microwave, we're pumping it in, water molecules all start rotating, they start hitting each other, creating randomized kinetic energy, right? And this is heat. This is why, for example, if I microwave my burrito, for certain parts of it heat much better than others. And it's because those pockets of coldness are where you have a lot of oils, things that are non-polar, that are not going to mix well with water, right? And so there's no water there to heat up, and I end up with cold, right? Okay? I need water to heat for a microwave function. Okay? Okay, so what if I do a metal object in my microwave? Put a fork in it. Sparks. They know why that is. And let me give you an even better question. Who predicted that? Before microwaves existed, in fact. So that's Einstein's first great discovery, actually. The first one that was ever proved, in fact. Okay, that's what made his name, his career. Is he predicted that effect, and that effect is that same trend that people taught you in the periodic table. Remember how the metals lose electrons with less energy? So what's happening is when you put metal into the microwave, it gets hit by this microwave radiation. With water, it just causes it to spin. Okay? With metal, it actually pops the electrons off of the metal, and those moving electrons is what we call electricity. Okay? And so it ejects the electrons from the metal. And that's the frame shift that happens with a metal versus a non-metal. The things in between are where you start getting a little bit different properties. So for example, you've seen the containers that have metal like lips and stuff. They're made of metal mixtures that are less frame shifted. Okay? And so don't eject electrons in a microwave. So vibration, everybody remember infrared radiation? Yeah, no, maybe? You've heard of IR, right? Infrared? Okay. It's the energy that has, it's the electromagnetic radiation that has less energy than visible light, which is right here. Visible light being the stuff you guys see. And so it's literally infra below red. Less energy than red. Okay? Anybody ever heard of terahertz? 5G? Okay. That's right here. Right on the line. Okay? It's this little band that's right on the line between infrared and microwave. And they didn't think had any unique properties, and now we're kind of learning it does. And so we didn't split it out in the original diagram. And whoops. Now, a funny thing is a bunch of physicists wrote grants based on this. It's been a big field of study for the last 20, 30 years in physics. And chemists had been studying this field for 130 years. It is called far infrared. And then the physicist somehow did not know this and did not look this up and wrote it as if it was a new discovery in 2000. Which is such a... so silly. So what infrared is it's a molecule, an organic molecule is going to vibrate. Okay? Think of it about like a spring, okay? You hit a spring... And so that's the sort of relationship you're going to see with infrared radiation to organic molecules. This right here is the visible light spectrum. You will note the visible light spectrum has no thing it does that's different than ultraviolet. It's low energy ultraviolet. That's what it is. Okay? Maybe a little bit over into the infrared in terms of properties. Can anybody tell me why there's a visible section that's been split out? Because most humans can see in that region. That's it. All right? And even that is kind of BS because there's a wide variety of ability to see in this region. For example, ladies can see a lot further in this region, and it'll differentiate the colors much better. And there's something called hyperchromism that happens in about 0.1% of women, where they can actually see up into the ultraviolet and down into the near infrared, which right here. Men, on the other hand, we're really lucky if we can see this whole region. And in fact, about if I remember correctly, the number somewhere in the 20 to 30% can't even see the whole region. So, we get shafted there, I guess, but that's okay. Now, the ultraviolet region is where you're going to start seeing things move up and down the orbitals. Remember when we were talking about the orbitals, the 1s, 2, 2p1, that sort of thing? Okay. That's where we actually move electrons among those orbitals, right? Now, having said that, because it moves it along the orbitals, when you have molecular orbitals, it moves them along the molecular orbitals, doesn't it? Okay? Remember our molecular orbitals? There was bonding and anti-bonding, wasn't there? Some things don't have a lot of margin, do they? If you move a single electron up into an anti-bonding orbital, it's not going to be bonded anymore. And so when you start looking at these higher energy ultraviolet radiations, you can actually start getting it where it starts causing reactions in organic molecules. Where like it'll bust open bonds and then things will bond to other stuff. Okay? And remember the HV, where we looked in organic chemistry, it said HV? That was high frequency light. That was high frequency UV radiation typically. Sometimes it was blue light. Sometimes. But those actually were causing reactions by usually homolytically busting open bonds, right? Because it transferred electrons up into anti-bonding orbitals, made them unstable, and they came apart. Whoa, huh? I know, it's like these things actually had reasons. Okay, and so if you get past this, you get into the X-rays. Yes, it's X-rays as in I shoot X-rays at you and see an image. These actually cause bonds to break and ionize. And so you'll actually, for sure, break bonds and ionize them. It doesn't just take unstable stuff to do it. Okay? And so you can smash apart a lot of stuff with X-rays. It's a very common method for things like GCMS that we talked about. This is a fairly common way of doing that. Okay? This right here is gamma rays. Honestly, at the point of gamma rays, they're so damn high energy that they just nuke whatever hits them. Sometimes literally because they're from a nuke. And they're incredibly high energy. This is not necessarily the same thing as cosmic particles, by the way. Though gamma rays do come as part of cosmic particle collisions and come with cosmic particles because fusion causes gamma rays as well. But they're so high energy that they rarely ever get down to the planet itself in terms of gamma rays. And when they do, the amount has been lowered so much because they've smashed everything apart on the way in. Okay? And they get used up when they smash stuff apart. So, the planet largely protects us from this. This is one of the reasons, so when you go out in space, gamma rays can penetrate through lead. You have to have several feet of lead, usually, to block the gamma rays. And so when you get out in space, a spacecraft that could go to Mars, for example, everybody just die like within a month of getting to Mars because they would have been bombarded by gamma rays and cosmic radiation particles like high energy neutrons for the entire trip without a very, very heavy ship to protect them. So, very difficult problem. All right, so this right here is how wavelengths work and how waves work. Okay, so normally when we're doing in the bath, right, we can play with our water, splash, splash, splash. And if we get the right tempo for splashing, has anybody done this before? you can actually generate a standing wave, right? And it will go more and more and more as you go. And the amplitudes will get very high, right? Okay. And so what these are is it's a constructive interference between two waves. And what ends up happening is the amplitude is the addition of those two amplitudes of the individual waves. Okay? And that's called constructive interference. All right, anybody ever failed to do that? After a while, you start getting the beat wrong. Okay? And it starts like breaking it up into this chop, right? And eventually it just sort of cancels out and you get almost nothing. Okay. That's destructive interference, right? And so what happens is a height, a maxima, is at the same point as the other's minima. In this case, our amplitudes are equal, and so they will perfectly cancel out. Anybody use noise canceling, active noise canceling? That's what they're doing, but for sound waves. Okay, you can do the exact same thing with light waves. You've all seen it before because you've all used flashlights, or you actually can see it when it's dark in here and you have these lights here. And what you're seeing is you see very bright points and then dark and then bright and then dark, and you see these like rings that go out, right? And that's actually constructive for the bright, destructive for the dark, and so you're getting then the medium ones are actually the original light source intensity. And that's what you're seeing is those concentric circles. Yeah. The wavelengths are being reflected off the back of the flashlight and overlapping differently, right? Yeah. Okay, so let's go ahead and look at that in terms of monochromatic planar wave. This is typically generated by a laser. I don't think they really do this much. LEDs as well, if they don't like purposefully not do this. Okay, if you're just having LED and they've done nothing else, you're gonna get this. You're gonna get something very similar to a laser and a monochromatic planar wave. Okay, this is actually why, for example, if you take your sunglasses, anybody have any sunglasses? And most phone screens, and then move the sunglasses like this, you can actually start blocking out a bunch of light. Okay. Now, having said that, it's actually harder to find screens that will do it because they have the OLEDs now, and they've done a bunch of stuff to make that not happen anymore. Okay. So they've screwed up my example by trying to get to be good. For example, it doesn't work so great on this screen anymore. You can take pictures of this screen pretty nicely because it's an OLED, very high resolution screen. Yeah, they've gotten good. Damn them. So anyways, these interference or diffraction patterns actually become very obvious when you look at these. And so when you have two monochromatic beams of light that pass through a screen that contains two narrow slits, right here we see the narrow slits. These are typically slit or diffraction. This is why, for example, if you ever look at a eclipse, one of the ways you can do it is by looking through a small hole. You're actually making slits like this. Okay, you can actually do this experiment if you want, by the way. If you get a really nice monochrome under like a blue LED, that sort of thing, you can actually put it next to two holes in a piece of paper and it'll do this. Okay, or two slits also works. It's just harder to do slits. Two small holes usually is easier. What you'll see here is that they will have a pattern of constructive and destructive interference that will come out right here off of this optical screen. This optical screen can be something as simple as a thin piece of paper, or it could be something more complex. Essentially, it's an object for the beams to hit, reorient, so they're all moving in the same direction. Okay? And what you'll see is you'll actually see banding that happens from this, and those will actually correspond to these energy levels right here. This is actually Thomas Young's double slit experiment. It actually is what demonstrated the wave-like nature of light. It's an extremely famous experiment and a great example of testing the properties of something. Okay? Very cool. Okay, everybody okay with that? Everybody understands why that demonstrates wave-like nature? If you don't have waves, can you have destructive and constructive interference from this? No, you have to have wave properties, don't you? Yeah. Okay. So this is the illustration of the electron accelerating towards the nucleus in a planetary model of the atom. And remember, this is one of the original sort of Bohr model of the atom, where it was a planetary rotation, like the planets rotate around the sun, right? Okay. Is that model correct according to what we know now? No. Why the hell am I teaching you an incorrect model? Okay. In terms of mathematically, why do things absorb the light, the wavelengths they do? In terms of understanding them mathematically, this is a very, very useful model to use in your head. Okay. Are these atoms actually in orbitals? No, they're not in orbitals. Okay. But they are in energy levels, right? Which in many ways is like orbitals. Okay? And so we still refer to these as orbitals, even though it doesn't necessarily make a huge amount of sense, right? Because we're already using energy level for another part of this. Okay? Those are the periods, also referred to as energy levels. Okay? And so we had to subdivide this with some sort of language. In terms of models, this actually makes a lot of sense when you start looking at the math and how this actually functions, how it actually like works on a large scale. Okay. Okay, so this right here is the line spectra of your elements. We have lithium, sodium, calcium, strontium, and mercury. Again, this is from a spectroscope. Essentially what this is we're energizing a pretty pure sample of this, and then we're putting it through a prism, so it subdivides the different frequencies of light, and then what we get is these bands of light. Okay? In this case, these don't necessarily have to be visible, by the way. We can have spectroscopes that will actually subdivide them, and these colors are kind of just so you can see it. They then do things to different parts of the band to make it visible. Oftentimes when you see these things, this one I believe is all actual the colors. By the way, does anybody know what black and white actually mean for your eyes in terms of light?
All light with the absence of light.
Exactly, yeah. So white light just means that I have enough frequencies in there that my eyes are going, I give up. Okay? And black is where I don't have enough light to really be able to deal with it. And so my eyes go, I give up. Okay? And they're just your eyes going, whatever. This is also why black and white in your brain can actually get switched. Okay? So if you ever look at objects, you can actually start seeing all white or all black in different areas. Or you can actually invert the black and white in an object. Okay? Okay. So these right here are the different wavelengths. This one's just visible light being shown. And so we're energizing these samples. And what we're seeing is lithium gives off 4 frequencies right here. And so that right there is the line spectrum for lithium. This is actually how you go like, we have this amount of this substance on this planet or this star. Okay, stars are easier because lots of light coming off, right? But planets can also be done. They're just a little more difficult. This right here is a gas discharge tube. Here we're actually doing the line spectrum of hydrogen. So that's what you see with your eyes, from a picture of it at least. And this right here are the actual frequencies that come off of this in terms of the line spectrum for hydrogen. Now, what do you think these lines represent, they match up with? Electrons, yeah, but not just electrons, but where they are, right? You can think of these as the, if you're using the Bohr model, these would be the different orbitals, the different distances from the nuclei. And so each of these lines is going to represent an electron jumping from one orbital to another orbital. Okay? And that's what they represent, is moving from one orbital to another. Okay? And so you get a jump from, say, orbital 1 to orbital 2, and then orbital 2 to orbital 3, and then you can get the jumps from orbital 1 to orbital 3, and that'd be a higher energy one, right? Higher energy ones are represented by what wavelengths? Larger wavelengths or shorter wavelengths? So short wavelengths are higher frequency, higher energy. Okay? Longer wavelengths are lower energy, lower frequency. Okay? So for example, this red one right here, that's low energy. Okay? This one over here is high energy. These ones are quite high energy. Okay. All right, so in terms of formula, this is actually the formula for figuring this out. So if we calculate the longest wavelength in nanometer line in the Balmer series for a line spectrum of hydrogen, if NF equals 2, what we would do is the orbitals will go in here. This is a constant. This right here is the wavelength. Okay? This right here is Rydberg's constant for hydrogen. There would be a different one for each of the elements because they have different nuclei. Right? It'd be like different planets have different gravity, to use the orbital analogy. Okay? Okay, and so we go ahead and substitute this in. This one's RH right here. This is 1 over 2, and then we square that number, minus 1 over 3. We square that number. And then we go ahead and solve this first. 2 to the second power 4, right? 3 to the second power 9. We do these, 1 over 4, 1 over 9. Mm-hmm.
What is that? NF squared and NI squared? How do you get the 2 and the 3?
Final and initial orbital.
Oh, okay.
Yeah.
Okay.
Yeah. So these are going to be the same n. Remember your orbitals. Okay, so when we learned our orbitals, those n numbers, they were corresponding to periods on the periodic table, right? They were the energy levels. Okay? And so what we're seeing here is we're dropping down in the energy. We boosted something up. We drop down from the higher energy orbital to the lower energy orbital. Now, if we boost something up, we use the energy, right? And so light doesn't come out. That's absorption. If something drops down from a high energy orbital, orbital 3, to a low energy orbital, orbital 2, then we're going to emit the energy. Okay? And so what we're seeing here is an electron in the hydrogen in orbital 3 dropping down to orbital 2 and emitting the lowest amount of energy we can emit. Okay. And so we go ahead and solve this, multiply it by that. That's going to give us 1 over the wavelength. See that unit right there? Centimeters negative 1. Okay. That unit right there sets the units for our wavelength. Okay. So if you're ever wondering, what would my wavelength come out? Nanometers, centimeters, meters, whatever? The constant. That's where you should always get that, okay? Okay. And so this is 1 over wavelength right now, so we need to go ahead and invert this. And so we take 1 over this number, so we can flip it, right? And get it up on the top, so we have wavelength. And then we're going to go ahead and do the math to get the centimeters into nanometers. Okay. Everybody good with that? Did I lose anybody?
Can you explain one more time why N1 or Ni is 3?
Yeah. So this right here is going to be our longest line. Is going to be the value that's closest to the value of NF. Now, when you go up in orbitals, you have less interference happening, less pull from the nucleus. Mm-hmm. And so the 3 to 2, we need to use a larger one for the NF. Mm-hmm. Okay. We know that this has to be 2 here. Mm-hmm. So the one that's going to give us the smallest energy difference there is going to be the one immediately above it. Okay. We could theoretically, if we wanted to get a larger difference, use a 4. Mm-hmm. 4 going down to 2. but it asked us for the smallest.
Okay.
Is that making more sense?
Yeah, so it's always just going to be one above it, just depending on
If it's the lowest energy, yeah.
if it's the lowest. Got it. Thank you.
Because that will give you the least amount of energy that'll emit. Yeah.
Thank you.
Like if you had designed a hydrogen lamp, okay? By the way, sodium lamps are those yellow lamps that you see in the street walks, in case you're wondering where this shows up. So if you were designing, like, say, a hydrogen lamp, okay, and you wanted a specific color to come out, what you can do is you can actually design your energy you're putting in to boost the electrons to an orbital, and then that orbital, then you calculate the difference, the wavelength that would fall down. And so you could actually, by boosting it to higher energy orbitals, change the light that's coming out. Yeah. Or you can use it in reverse. I'm seeing this light come out. What energy do I have to have in there to do that? Okay? No problem. No. Okay. So this right here is some of the different lights, the schematic diagram of different series is in the line spectrum of hydrogen. And so here we see the ultraviolet region. This is ones that have ultraviolet. You wouldn't be able to see them with your eyes usually. And so this right here is called the Lyman series. This is the Balmer series. This is actually the one that's in the visible light spectrum. The Passion series is this one out here, which is the first one that was in the infrared. And then the low infrared was actually the Bracket series right here. And so these were all done as the detectors became capable of doing those spectrums. Okay? Keep in mind that the Balmer series here is the only one that you can see with your eyes without anything else. Right? Everything else you have to use some sort of shift or detector or something to shift it within visible light so you can start seeing it. Yeah. So you can shift all the frequencies if you wanted. That's possible. That's how the old style IR goggles worked. The heat detector goggles, like that you've seen in the military movies and stuff. Yeah. That's why they had those like greenish tint lens. Yeah. Okay. So this right here is the spectral radiance. And so the spectral distribution of radiation has a function of wavelength. This is for 3 different temperature stars. So a star is going to be one of the closest approximations to a perfect black body radiator. Black body radiator just means that it doesn't absorb all the light that gets absorbed back in comes back out as its emissions. It doesn't reflect anything. Okay? It would be problematic if it reflects things, because then it's reflecting the light that's coming in. It's not just the light that it emits, right? Okay, know that a lot of equations are done with a black body model or a black body radiator. Stars are about the best black body example that we're going to get in the universe, though there are some pretty impressive synthetic ones that they've made. This is one of the reasons they do things like try to make new paints and stuff, new colors that are more perfectly black. And spend like $10 million doing it so they can isolate and not have refracted light off of the signal. Yeah. So this right here is at the different temperatures. What do we notice as we increase the temperatures? So again, this is hydrogen, like a star, right? And cool stars have frequencies that are more in the red colors, and actually the majority of light are in the infrared, aren't they? Okay. When we get hotter, younger stars, then that's going to be more in the visible light region, right? And so we start getting colors that are more like orange and red, right? Okay. And so when we start getting hotter stars, like a 5,000 Kelvin star, it's yellow. What do you think our star is like? What color is our star? Yellow. And so the temperature is around 5,000 Kelvin. Yeah. There you go. And that's actually the line spectrum distribution of the star can tell us that. The approximate temperature of it. Okay, so the properties of light again. Photons are what we consider the particles of light with energy. This is actually going to be the energy of the photons. This is actually that same relationship I had been talking about just a second ago, where I was talking about high frequency, high energy. Remember that? Low wavelength, high energy. Same relationship. So this uses Planck's constant right here. Planck's constant gives me nightmares. This damn number is, this tells you things about the universe that are just disturbing. Okay? Like there's a joule second distribution of energy in the universe that is enforced by the universe laws. And so this limits things on how they propagate. This is the same relationship and constant that tells us like this things can't go faster than the speed of light. This ends up being related to. This ends up being related to like how electrons pop in and out of the damn universe. Yeah. And how all particles actually have wave properties. Anyways, you guys don't need to know a lot about that yet. But Planck's constant here times 1 over seconds, which is the frequencies, gives you joules, which is energy, right? By the way, do you guys know how many equations I memorized, formulas I memorized when I was an undergraduate? 3, maybe 4. And why I did that is because I have to give you the constants on all the exams, right? If I have the constant here, how do I get joules energy out of that? Multiply it by 1 over seconds, right? Or divide it by seconds. What number do I know that's 1 over seconds? Frequency. So I can derive this equation from this constant almost immediately, right? If I ever forget or don't understand what I'm looking at. Okay? Okay, so if we combine the equations I've given you so far, remember that C equals frequency times wavelength? Okay. If I combine these relationships, then I actually can get energy as related to things like wavelength, can't I? Okay. And so, for example, energy equals H, which again is my Planck's constant, C, which is again a constant, the speed of light, times the frequency here. This one is divided by, and it's the wavelength. And that's why, for example, these are inversely related. These frequency is directly related, aren't they? Okay. That was the relationship. Anybody have any questions about that at all? No?
What is C again? It's the
Speed of light.
Oh, yeah.
Yeah, speed of light in a vacuum specifically.
Right. So
Which
in
is not really different. It's just how you measure.
in that example, it'd just be like the only number you really plug in is the 147
Yeah.
on the bottom, and then everything else is a constant.
In fact, there's actually a like people that work a lot in light will actually have, like I used to have spreadsheets where I just had HC already calculated. Just plug in the one number. Or like I have a saved function on my calculator, saved number. Like it just got second dink, and that was HC. Because they're so dang heavily related. Okay, so notice that classical theory right here for 5,000 Kelvin, that damn thing's not even on the graph, is it? See that? We blew right through the graph, didn't we? That's not right. That's very wrong. And so what is the difference between classical theory and Planck's hypothesis, or quantum? This is actually where quantum mechanics comes from, quantum chemistry, quantum theory, blah, 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 quantum. And it's literally that energy levels are quantized. Okay? There is no every number between 0 and whatever. Okay? It's quantized. It's like a staircase. There are specific energy levels that you can be on. You can't be anything between. Okay? And so this is, again, the classical physics. It's the equipartition of the energy levels, where you can be any energy level between. If you have a substance, it can absorb any energy level. Okay? This right here is, again, the quantized energy levels. If you have a substance, it can only absorb specific energies, and it can only emit specific energies. Can these be quite complex and have a lot of quantization? Yes, most definitely. Okay, for example, metals are notoriously bad for this because they end up with very, very small stairs. Okay? You can think of it like a staircase. Have you guys ever seen that where they do the very tiny stairs? They end up stepping on multiple stairs at any given time. Usually around like water parks and stuff because it makes it harder for you to slide. Okay. Right? That's like a metal. They have such small separations of the energy states that it almost looks like a classical physics case. It's not, though. It never is. They're always quantized. Okay. Now, having said this, can you jump up 2 stairs? Can you, like, just jump down a staircase? Hopefully not the ones here, but like a 4 or 5 staircase. Yeah. People do that all the time, right? And so, yes, you can do stuff like that where you jump up multiple stairs, you drop down like 4 or 5 of them. Yeah. That's totally doable, okay? And we've only discussed parts of the quantization of this electromagnetic radiation and of these energy levels. Like there's multiple things that you can excite all at once. Okay? Okay, so let's calculate the energy for the longest wavelength line in the Passion series. I always say their names wrong, but that's okay. They're all dead as far as I remember. So, NF equals 3. So we're going to calculate again the wavelength of the line using the Rydberg equation. That's this one right here. We'll again use the value right here, our H. And again, we have NF that we've been given, and so we plug that in. If we're emitting energy, then that has to have been a higher energy level when we started, right? Okay. By the way, you can use this equation either way. So if we were taking up energy, absorbing energy, you'd have a lower number, the Ni, the initial state. Okay? Okay, so we plug those numbers in. We go ahead and solve the equation. We'll get an inverse wavelength. We go ahead and plug that in 1 over the number we got. We convert that to nanometers, and we get the Passion series number for our emission. Okay? Now, if we want that in energy, joules, we need to plug that into E equals Hc over wavelength, right? Okay. And so we go ahead and plug that in. Now, funny enough, we did this so we could get the nanometer number and you guys could relate this in your heads. But it's not always smart to just convert everything to nanometers all the time and just do automatic conversions. Okay? We actually started with a 1 over centimeters number right here, didn't we? We could have plugged that in after we converted it to meters, couldn't we? And saved ourselves a hell of a lot of work. Can everybody see that? Yeah. Yeah, so we actually could have saved ourselves like, 3 steps in terms of our putting it in the calculator? By just taking this number here and going into meters. So, yeah. So keep in mind that you don't have to get nanometers every time if the answer's only asking for joules, okay? Like, you don't have to go to specific things. This is not formulaic. Again, it's math. Math has many pathways, right? So, if you do need to go to certain things, and you do think very formulaic, then it's fine. You're just going to take some extra time to do it, okay? It's not an issue, though. Okay, does anybody have any questions there? Are these numbers going to be very large, typically, when you're talking about joules for these numbers? No. No. You're getting hit by moles of radiation every second. if they had even single joule numbers for a photon, the whole planet would be gone within nanoseconds. Like one wave of light hits us and boom, it's gone. Because we're getting hit by massive amounts of photons, right? So these have to be very small numbers. Okay? Okay, so keep that in mind when you do the calculations. If I calculate the weight of a feather is the weight of a sun, then something's wrong. Okay. So this is actually the energy level diagram that's shown for different series of lines in the line spectrum of hydrogen. You can see the different series and their different energy transitions. And of course, these are all the emissions. You can also do absorptions just going the opposite way. Okay, everybody good with that so far? Okay. And remember, these lower energy transitions right here, those are your infrared, near infrared, visible, ultraviolet, right? See how easy that is? Yeah. Mm-hmm.
So you just assume that the initial is always one higher than the final.
No, it does not need to be. In these cases right here, we are always the longest wavelength, lowest energy, one of the two. And so the closest one has to be lowest energy because they go up from that. Because you get further from the nucleus, meaning higher energy. Same as like space, right? It's harder to jump up past the planet than it is to jump up a foot, right? Yeah. And so, like, you very well could be given, and it very well need the number going from NF is 2 and NI is 5. But it would indicate that in some way. Okay? And keep in mind that this N, this is can go to infinity. Theoretically. In practice, eventually it would go off to popping off the electron and there'd be no more difference after that. Okay? But theoretically speaking, you'd move it far enough and it still has some sort of attraction between it. That would be infinite N. Okay? Okay, this right here is actually the emission lines in the line spectrum as observed if you took a Bohr model of the atom. This is actually why the Bohr model still exists and you still see it and it's still very useful. Is because it actually graphically does the same thing as a diagram like this does, but in a format that looks like an atom and is easier to understand, right? And realistically speaking, these are pretty analogous, these Bohr model orbitals, to the distance from the nucleus. Those distances being the shells. Remember the shells? Now, do the shells have nice orbital shapes? No. No, they do not. Okay? And partially that's because you can never be sure where an electron is, because it's always popping in and out of existence. Okay? But it's a great mental model to use when you're doing this stuff. Honestly speaking, you're better off just using a Bohr model in your head and doing everything like it's the Bohr model. Because otherwise you just get complex and confused, right? And it's not helpful. Okay, now the radii of the circular Bohr orbits actually goes as n squared a0, where a0 is actually the Bohr radius, which is 52.9 picometers. Okay, and so these would be the sort of distances you would see. A0, this is that right there. It's the first orbital for the nucleus for hydrogen. Okay. And then you'd get 4 times, you'd get 9 times, etc. Everybody okay with that? And that's why the energy differences become so much larger. Is because it's not a doubling each time, right? And that's why you don't have a consistent just like it's double each time, it's triple each time, something like that. They end up way higher energy, right? Okay. Okay, so this is the wave-like properties of matter. I know. Has anybody ever heard that there is a wave-particle duality? Yeah? No? Maybe? Okay. So for electromagnetic radiation, it's very, very, very wave-like. Is there some particle properties? Yes, a little bit. But they're very hard to find, and you're not going to encounter them unless you start getting into some very special cases. So you can essentially treat them as waves, no problem, whatever. Okay? Good enough. When you start getting into particles, if you're talking about something that has a bulk mass, a macro particle, okay, a macro object, like a human or a cell or, hell, a molecule, you're going to experience very little wave-like properties. Okay? For the most part, wave-like properties is not going to happen. Cool. You start getting smaller and smaller, less and less mass, you're going to get more and more wave-like. Okay? You get into electrons, they have a lot of wave-like properties. Right? That's why we can't pin them down to an orbital, because the damn things are waves. Okay? They have probability distributions. They don't have a fixed location that we can actually detect. Okay? And so, yeah. This is the schematic diagram of the Davison-Germer, I think it's Germer actually, if I remember correctly, experiment. Honestly, I don't think the names really matter that much, but might as well give you the people's names, right? This is the electron gun right here. We shot a beam of electrons at a nickel crystal. And what we get is the scatter beam coming off the nickel crystal. And over here we have the movable detector. By the way, in case you guys are wondering why there's like these no title things in here, it's because they didn't provide me any other diagrams or anything for the book manufacturer as files. So I literally have to scan out these figures from your book. Which is such a pain in the damn ass. I guess it's better than, I've had a book before that gave me the diagrams, but they were all rough draft ones, and they changed all of them from. And so there was errors all over them. That's actually less useful. Okay, so this is actually how this formula comes together. Remember that P here is momentum. That equals the mass times the velocity. When we start getting into particles, we have mass that's actually large enough that makes some sort of difference, right? For example, a photon may not have any resting mass. Okay? It has mass when it's moving because it's moving near the speed of light. Okay, it's relativistic mass. Or another way of saying it is it has energy that's exhibiting mass. Okay? Anyways, this right here is your scattering. Remember, E equals mc squared. Everybody's good with that one, right? Okay. And then we have the wavelength equals h, which is our constant, times the speed of light, divided by E, which is the energy. We can relate these terms, and we see that Planck's constant over momentum, or Planck's constant over mass times velocity, actually gives us wavelength, doesn't it? Okay. But what do we notice about this wavelength? As mass gets larger, what happens to our wavelength?
It's smaller.
It gets smaller, yeah. And mass gets larger real fast when you're talking about electrons versus nucleus, right? And then you start talking about molecules and like 1 kilogram of weight versus a proton, right? Mass goes up real fast from subatomic particle to like a cell, right? And so what we see here is once you are small enough that you're something like an electron, this wavelength is large enough that you can actually start seeing effects from it. Like if you were to play, if you were to play football, if you were to play baseball, let's do baseball easier, and you were to throw a baseball, and this number here was large enough that we exhibited electron-like properties with a baseball, what we would see is you never know if you're actually going to get a strike or a ball, because it would just fully pop into the catcher's mitt sometimes, and sometimes it would pop over the base and it might miss the catcher. And that's why like wavelengths, electromagnetic radiation can go through walls. Okay? That's why, like, the Wi-Fi we're getting here, despite having no Wi-Fi hotspot in the same room, right? Is those wavelengths are large enough that a lot of the expression happens past the walls. And they do go through them, but that going through is more like zigzagging because of the electromagnetic fields, not going through the atoms. Okay? It's a bit different. Okay, so when we're talking about all matter in the universe, in reality it had wave-like properties. It's just the wavelength of those properties, the frequency of those properties is so high, the wavelength is so low that, you know how like a movie looks like a constant thing? But it's in reality like 60 frames a second, right? It's like that. It's flickering so fast we can't really, it's not meaningful to us whenever we're talking about like a nucleus of an atom or a cell or you. When we're talking about something like an electron, it's flickering slow enough in and out of existence that we can actually see some of those wave properties. Okay? Okay, so this is actually just the equation for this. I don't think you guys really need me to work this out. We're just plugging each of these things in, okay? Keep in mind, though, you got to match your units. And this is one place where it really, really helps if you have what a joule actually is. Okay? Because what you're seeing here is we're actually breaking down a joule. So we're breaking the units down for a joule when we're doing this formula. That's where that kilogram and the meter second here goes. We're canceling out one of the meters. This second here is canceling out one of the seconds here in the joule. And this second is canceling the other second out. Cancel out the kilograms in the joule, and we're left only with meters. Yeah. So we're actually canceling out the units within the joule, which is a derived unit. Okay. It makes these problems real easy if at the beginning of an exam, if I haven't given you what a joule is, which I probably will, but you write down what a joule is. Or you have that. Anyways, this is like for a 142 gram baseball traveling at 100 miles per hour. We convert the velocity to meters per second, convert the mass into a kilograms. We plug that into the formula, and we get that right there. Our wavelength is 1.04 times 10 to the negative 34. What that means is that ball is actually popping in and out to existence, the particles in it, at that wavelength. Okay? And it's doing it in all sorts of directions, just not just the path it's taking. Okay? Some of that wavelength is being devoted towards the path it's taking. And this is one of the reasons why when we start moving at relativistic speeds, we actually start consuming all of these cycles that would normally be randomized and just going straight forward. And anybody ever heard of relativity? Okay, as you get closer and closer to the speed of light, what happens to your time? Slows down. And this randomized distribution of probability that's happening because of this Planck's constant, this is actually what your time is. And if you consume it all in going one direction because you're going the speed of light, you no longer experience the randomized distribution, which is time. Anyways, that's not really a topic that's in this course. It's just an interesting topic. And it's deeply disturbing and will give you nightmares. So let me just destroy your idea of the universe right here. I know, it's weird, right? Okay, so this is the circular standing waves in the quantization of angular momentum. And so when we start looking at particles, one of the ways that it's actually easier to understand particles and understand their wave-like properties is by envisioning them as standing waves. Anybody ever heard of string theory? Yeah? Okay, probably bullshit, but what it is it's based on these ideas so that you think of them as standing waves or strings being vibrated, right? Okay? And that's kind of the useful thing. It's a useful mental model that when you start going really deep in the math here is helpful. Okay? But we're not going to go that far. We're not even going to touch string theory. Don't. So throw that out of your heads and let's go on. Okay? And so what we see here is that when we're looking at a standing wave, everybody knows what a standing wave is, right? Remember our bathtub example? Splashing the water, and it gets higher and higher and higher as we go. That's a standing wave. The peaks were all in the same places. The troughs were all in the same places, right? So it's a standing wave, but standing waves are not actually staying still, right? They're actually bouncing back and forth and reinforcing themselves. Okay? Okay, so we have our standing wave right here. One of the best examples of standing waves is actually in an amphitheater. Anybody ever been into a nice concert hall or amphitheater? Or one of those whisper corners? No? Okay. It's where it can very easily create standing waves of sound. And so what happens is you get a huge amplification of the sound, even though the input is very quiet. For example, I used to teach in KU. They had brand new lecture halls that they had set it up to be amphitheaters. And so I used to teach like this and talk like this. Can you guys even hear me? Yeah, kind of you. Anybody else? And I could teach like this. So I could teach in almost a whisper and in a class of 100 students be perfectly heard by everyone. Yeah. And that's because the position I was in occupying set up standing waves across the classroom. Yeah. Anyways, this right here, standing wave, the harmonic number is in. The second overtone is 3. You get 3 times amplification. See that? And so this is the first overtone is 2. This one here is the fundamental 1. This right here is the length that we required. It's going to be matching wavelengths. So for example, this one right here is 3 times the wavelength of this wave here. And so we need to match those wavelengths 3 times. And we get the second overtone 3, right? Because these are the overtones. Okay. This right here, 2. This one's 1 because we exactly match the wavelength. Okay. Anything that does not match the wavelength is going to create chop. Because your waves are going to bounce, and then they're going to start canceling parts out. And this is actually why, have you guys ever seen like the noise canceling environments? You guys ever seen music being recorded? No? Not on a video or anything? Or the noise canceling or signal canceling environments they test like phones in and stuff? And they have like these foam panels that are on the walls, and they're like these weird geometries that look like some sort of nightmare. Yeah. What they're doing is they're actually causing it so there's no standing waves that can be created. They're making it so every deflection does not give you a standing wave, and it breaks up whatever waves are coming in. Okay? And that's what they're doing. And hopefully it cancels everything out if they've done a good job. Yeah. Okay, anyways, these right here are some different... this is a linear guitar string, by the way, if you're just... and so they make the guitars so that it has a standing wave that it creates within the cavity of the guitar. Okay? And that's why you get that amplification of the sound. This right here is going to be the first 3 circular standing waves made by taking guitar strings, wrapping them in a circle so that their ends connect. And so again, you can actually create standing waves in circular formats. Or you could create them in atoms. Okay? All right, so this is actually the classical wave equation. See all that calculus stuff? There. Okay, magic. All right, everybody good with that? Just understand that how you calculate out where the orbitals are, what they look like, how these electrons move in them, that's these wave equations. Okay, it's calculus. It takes partial derivatives, which I believe is Calc 2 or 3 here, right? Calc 2 probably. Okay, and yes, this class does not require those, and so magic hand wave. Calculus was done by someone. Okay. Okay. If you want to learn it, it's in the book, and we can talk about it sometime. But it's just beyond the scope of this class. Okay. Okay, so let's talk about the particle in a box model. So if we sketch a one-dimensional particle in a box, it would end up with these as our variables. And so when we get beyond these particle limits of the box, what we would have is an infinite amount of resistance. Or another way of saying that is we can't go outside the damn box because energetically it's extremely unfavorable, right? Okay. And one of the problems was that when we start looking at things as waves, they aren't contained easily by boxes. That's just not how that works, right? So they need some sort of resistance to reflect backwards. They need to, it starts becoming more complex. Okay? Okay. So this right here is actually these first several solutions, the particle in a box problem. Honestly, you guys don't really need to know this stuff that much or even deal with this. But can you guys see that they're standing waves that we end up establishing? Yeah. And so when we start looking at these particles that have wave-like properties, what we start seeing is the more wave-like they are, the more likely it is you're going to have areas where they will express a lot. There's high probability of finding them, and areas where there's a very low probability of finding them. Does this sound like anything? This was the early work to discover orbitals. Okay, the modern day orbitals that we think of, where we have a 90% probability of finding an electron in this weird looking shape. Okay, and so what we're actually looking at is the standing wave structures from a particle in a box of that shape. Okay, or the wavelength functions. Okay, so these are the equations. We don't really need this stuff. This right here is the quantum mechanical behavior of nanoparticles. They're actually quite interesting because the size of the particle actually changes the wavelength that's going to be emitted. And so you actually get different wavelength particles from the different sizes of the particles. Neat, huh? Okay. This is very commonly done with like gold colloids or silver colloids. And so you know how there's that silver colloid people like to use on their skin, it turns them blue? It's actually what's happening is that's a nanoparticle. Okay. Yeah. All right. This right here would actually be, does anybody recognize this stuff here? NLML? Yeah, the quantum numbers. Remember those from Gen Chem? And so what those were is they were actually being created from the solved time-independent Schrodinger equation for that hydrogen atom, specifically in a spherical polar coordinates. And those are actually the variables in there. Okay? And so that's what you were seeing, the results of that. We'll get into that in quantum. If you end up having quantum with me, I think all of you probably will at some point. Or I've already had it, maybe. One or two. And so this is the principal quantum number. That's the number it matches up with the period, right? And so this is actually the energy or radius of that orbital. This right here is actually the shape. That dictates SPDF. That's the shape of that orbital. And nomenclature-wise, it's called the azimuthal. This right here is actually the magnetic number, and that gives you your orientation. Remember how there's 3 p orbitals? -1, 0, and 1? That's that. Okay? Okay, and then there's one last one, and that's actually the spin number. These are the s and p orbitals, by the way. as done in R, units of A0. Remember, that's that distance from a hydrogen nucleus. Yeah. And here's the shapes and what they look like. Remember, these are the p orbitals. I know, right? This is actually what it looks more like. This is a better representation of these in some ways. This is how they add them together to get that. And that's the d orbitals, by the way. Have you ever seen the d orbitals before? And there's the f orbitals. You guys all seen those before? They look really weird, don't they? Yeah. Because you have a lot of, at that point, you're really far from the nucleus, and you have a lot of interactions with the other orbitals. And so the magnetic fields get a little bit more complex at that point. Okay. We'll start up here next time. This is where I'll get into the spin quantum number. We got 3 slides left, so yeah. No, let's just start up here next time. Yeah. Yeah, I came really close, didn't I? Well, a little bit faster last week. Looking good. But I was